Okay, I think we're probably ready to start, Indranil, if that's okay with you.
Yeah.
Okay,
So go
well,
ahead.
good morning, good afternoon, good evening, everybody, in whichever part of the world, from whichever part of the world you're joining us, and welcome to this fifth session of this year's OSMU seminar, which today is being given by Indranil Banik. Indranil, who I first met just 2 years ago at a fascinating conference at the University of St Andrews, of which he was the chief local organizer. Very interesting conference on MOND to mark 40 years of the of MOND. He gained his PhD from the University of St Andrews, and then he worked for some 3 years with Pavel Krupa's group in Bonn. Sorry, it is in Bonn, isn't it, Pavel? I got that right, I hope. Yes.
Yes, that was in Bonn, indeed.
It was in Bonn, right. He went with for 3 years with Pavel in Bonn, and then returned to the UK, where he is currently with the Institute for Cosmology and Gravitation at the University of Portsmouth. And he's worked in many areas of astrophysics, but he's probably best known for his work on the hypothesis that the Hubble tension is the product of sorry, I beg your pardon, is the product of a local supervoid, and it's on that subject that he's going to speak to us today. So I hope I haven't left out anything essential, but I'm just going to hand over now to you, Indranil. Thank you very much.
Thank you, Michael. That's right. I am going to be speaking about the local void solution to the Hubble tension. So I'd like to thank the STFC for funding my PhD and also my previous postdoc, and the Royal Astronomical Society for funding a summer student last year who got some important results that I'll present in a bit. I'm at ICG Portsmouth now, where my work is funded by the Royal Society through a grant to my boss, Harry Desmond. So I'll explain what these represent as we go along. Now, briefly, before we begin, just like to mention that I'm organizing a parallel session at the National Astronomy Meeting in Durham this year. So that'll be from 7th to 11th July. Abstract submission is closed, but you can still register for the next month and a half approximately. So this is just a figure showing the various ways in which we chart the expansion history of the universe. Standard clocks, standard candles, standard rulers, gravitational lensing, also highlighting the possible role of large-scale structure in affecting some of these measurements, which I'll get onto more, but also with boundary conditions from the very early universe set by the cosmic background radiation. So although you can't contribute to that, you can still attend it. One thing you can contribute to, though, is our special issue in Galaxies on theoretical and observational approaches to the Hubble tension. So if you have like measurements of the expansion rate at various epochs, or if you have an idea on how to solve the Hubble tension and you want to review it, present the latest updates, that kind of thing, this special issue might be quite well suited for you. We'll not really set the deadline in middle of October, but we can extend that further. So this is about the Hubble tension as well. So without further ado, I'll try and briefly introduce what the Hubble tension actually even is. So the Hubble constant, first of all, is the present expansion rate of the universe. So the size of the universe is encapsulated in some cosmic scale factor A, which has the value 1 today. It was smaller in the past. And we're going to use a dot to denote a derivative with respect to time. So H in general is equal to A dot over A. A zero subscript just indicates the present value. So the Hubble tension is the fact that there's two different values you get for H naught, depending on how exactly you obtain it from the observations. So first of all, you can try to get the expansion rate of the universe by looking at the cosmic microwave background radiation and the pattern of anisotropies in it. So there are these tiny temperature variations in the cosmic microwave background radiation. And if you basically plot like a Fourier transform, essentially like a 2D Fourier transform of these temperature fluctuations, you get this characteristic pattern. So on smaller scales, which are to the right, there's generally less power, but there are these characteristic peaks. And these essentially arise from the fact that we think the initial density perturbations were set by inflation in like the very, very early universe, like within the first second. And by the time of recombination, 380,000 years later, an initial density perturbation could have undergone any number of oscillations. So the density perturbation initially would have created perhaps a compression, but then the pressure would rise and it would bounce out again, kind of like a spring. The number of oscillations will obviously be larger for oscillations on a smaller length scale because the period of oscillation will be shorter. On certain length scales, there will have been a half integer number of oscillations. And that's why you get these peaks. So here there have been half an oscillation, here there have been 1.5 oscillations and 2.5 and so on. So that's basically why, in a nutshell, you get the characteristic peaks in the CMB power spectrum. And from this, you can infer many cosmological parameters. You can infer the cosmological parameters of the lambda cold dark matter standard cosmological paradigm. Things like the matter density, how much of the matter is baryonic, how much is dark, but also the Hubble constant. Okay, yeah. Regarding the question in the chat, no, you would not be able to explain the CMB anisotropies without dark matter and dark energy. Also, one thing to understand, this H0 value you get is not a prediction by any means. It's a fit to the CMB. What I mean to say is by fitting the fit to the CMB shown here, that's a fit. That's not a prediction of ΛCDM. But ΛCDM with parameters calibrated in this way can be used to predict the expansion rate today, billions of years after we've observed the CMB.
I do apologize. I do apologize for butting in, but can I just ask? Not everybody may have seen the chat. Perhaps you could actually read out the question to which you're answering, or would you like me to read it out?
No, it's okay. I will try to answer the questions later on. I was just mentioning.
I was going to ask, do you in fact want to take questions during the talk, or would you rather leave it until the Q&A?
I think I'd rather leave it to the Q&A.
Okay, in that case, I should have asked you that before you started speaking. My apologies.
Sure.
Okay, so
unless it's urgent, unless it's something really unclear.
Leave questions till the Q&A.
But okay. Try and leave conceptual questions for the end of the talk, and then we can get back to this slide again, for instance. I don't mind that. Sure. But yeah, so the thing to understand, ΛCDM doesn't obviously predict the CMB anisotropy power spectrum, but if the parameters are fit to the CMB power spectrum, it can predict the value of H0 today. Now, then the important question, obviously, is whether this actually is the expansion rate today. So one way to try and estimate the expansion rate today is like this, right? You look at the distances to objects like galaxies, supernovae. You look at the redshifts from their spectra, and you get a nearly linear relation between distance and redshift. So you get a so-called redshift gradient, so dz by dr. Now, if this arises entirely from the difference in the scale factor A at the time of emission, when it was slightly less than 1, and at the time of reception, when A is equal to 1, then you can infer that H0 is equal to C times the redshift gradient. So I'll refer to this combination as just the local redshift gradient, which in principle is not the same as H0. We'll see why in a sec. But certainly, if the redshifts are entirely from cosmic expansion, H0 is equal to the local redshift gradient. The problem is there is a mismatch between the values you get from the CMB and from the local redshift gradient. So the CMB gives a value which is around 67.5 kilometers a second a megaparsec. or in inverse time units, like that would be approximately the inverse of 14 gig a year. H0, remember, is an inverse time scale. The local redshift gradient gives values which are around 73, 75 approximately kilometers a second a megaparsec. You can try to quantify that in lots of different ways using the so-called distance ladder, Cepheids, or tip of the red giant branch in the first rung. In the second rung, you can have supernovae, or you can try to get just one rung using mega mazes. So just geometric distances all the way. The fact that these all agree suggests that there is pretty good observational agreement regarding the value of the local redshift gradient, and it is not equal to the value you get from the CMB in the lambda CDM paradigm. So that's the present expansion rate and the Hubble tension in a nutshell. Now, just one thing I wanted to briefly show is regarding the local redshift gradient. In case any of you are skeptical that there even is a Hubble tension, this kind of illustrates how the local redshift gradient is built using a so-called distance ladder. So the ground floor, if you like, is the trigonometric distances using parallaxes, but also there's some other ways to do it, such as mega mazes. Then in the first rung, you have Cepheids or the tip of the red giant branch. In the top rung, you typically have supernova 1A, but you don't have to. You can build a 4-rung distance ladder. You can have fewer rungs with just Cepheids. So there's all these ways to swap out any particular element of the distance ladder that you don't like. You can use type 2 supernova instead of 1A, or you can use surface brightness fluctuation in the top rung instead. The point is, numerically, the values are all pretty similar. The Planck value for H0 would be around 67. So you can see it's definitely higher. The local redshift gradient is definitely steeper than predicted in lambda CDM, fit to the CMB anisotropies. You could also use data from the ACT telescope on the ground rather than the Planck on the CMB. So this is all pretty clear. And there is a Hubble tension. It's one of the most serious issues in cosmology at the moment. One thing I wanted to briefly show is if you try to infer constraints in the plane of the Hubble constant in units of 100 kilometers a second a megaparsec, so the Planck value would be around 0.67, and omega m, the fraction of the cosmic critical density in the matter, then this is kind of what it looks like. Okay, so first of all, this white dot and the error ellipse here shows the CMB based value from the Planck final data release. This red band shows what happens from constraints on the shape of the expansion history using uncalibrated probes. So without any absolute calibration, they only constrain A as a function of T over TU, where TU is the present age of the universe. They don't constrain the Hubble constant at all then. That gives you this red band, which provides a tight constraint on omega m. There's another way to get, well, you can also look at the turnover scale in the matter power spectrum, which constrains the product of omega m and h. And that's the green band. And the blue band is from the ages of the older stars. So you can see that they're not, they can't be reconciled within the 1 sigma confidence region. But at slightly over 1 sigma, you have this white triangle where you would expect the universe to sort of be. And remarkably, that's where the Planck data sits. Remember, these other 3 probes are independent of the any kind of model of the CMB anisotropies. So that's pretty good. The only discrepancy is the local redshift gradient, which sits up here. And that's clearly off. So then we can get okay. So the final thing I wanted to mention is that if you were to look at cosmic chronometers which measure Z dot by looking at stellar populations at different redshifts and quantifying the relative age between them, then you can get H0 as well, and that gives a value of H0 which is very similar to the Planck value. So remember, this is from somewhat higher redshifts, not in the very local universe where the local redshift gradient is measured. So at these somewhat higher redshifts, the expansion history seems to be following the Planck cosmology very well. But there is some kind of anomaly at low redshift. So then we get to why that might be. And one obvious possibility is that a local structure or a local inhomogeneity has systematically affected the local redshift gradient measurements. In short, the measurements are correct, but there is a mismatch between the redshift and the purely cosmological contribution to the redshift. This is obvious for galaxies like Andromeda, which is approaching us. It's blue shifted. That's not because the universe is contracting. It's because Andromeda has what is technically known as a peculiar velocity towards the Milky Way. On slightly larger scales, the peculiar velocities stay similar in magnitude, but they become proportionately smaller compared to the redshift because the redshift keeps getting larger and larger further away. So the impact of peculiar velocities relatively should become smaller further out because the cosmic contribution to the redshift is larger. That's true in general, but if we were near the center of a large void, then the outward peculiar velocity would rise at first because at the center of a void, there'd be no outflow velocity. The outflow velocity would rise, and then it would start dropping as you go very far away, and eventually there'd be no kind of net outflow. So there'd be a region in which the outflow velocity is rising, and therefore that would inflate the local redshift gradient, at least over some range of redshifts. So in short, the local redshift gradient would be skewed. And this might be causing the Hubble tension. So there is actually strong evidence that we are in a large local underdensity from galaxy number counts in the near infrared. They're not only in the near infrared, there's actually evidence all across the whole electromagnetic spectrum. But certainly in the near infrared, you've got galaxy number counts over 90% of the sky and most of the luminosity function. So this is a plot from the Keenan et al. 2013 paper showing the absolute magnitudes of galaxies and the proportion of the total luminosity across all galaxies contributed by galaxies in each absolute magnitude interval. So you can see that most of the luminosity comes from galaxies in a certain range, so-called L star scale, if you like. The observations are able to probe quite far down to quite faint galaxies. Or more precisely, we're able to cover most of the luminosity function, at least 57%, up to 75% in many regions. So what's shown on the right is the co-moving luminosity density. So this is basically proportional to the density of matter in arbitrary units. Don't worry about the actual units, but it's shown as a function of the distance. And you can see that there's this flat region, which is presumably the cosmic average. And then the density is lower near us, implying that we're in a large underdensity. So this blue point is an average across this range of redshifts, which is the one we were using to constrain our models. So that's basically the KBC void. So let me just see if there are any further questions. Yeah, okay. So that's the KBC void. Now, one thing to understand is the KBC void is observed, but it's not consistent with the lambda cold dark matter model. So we consider a uniform grid of 1 million vantage points in the MXXL simulation of ΛCDM, which has a 4.1 co-moving gigaparsec box size. And we try to work out the density contrast within a range of 40 to 300 megaparsec of each vantage point. And we compare the mass, but the density within that region to the density of the whole volume. What you end up finding is basically this blue histogram, which shows you the frequency distribution of the underdensity. Okay, so clearly on average, there's zero underdensity. That's the most likely scenario, but you can have some underdensity. You can also have some overdensity. But the important thing is the observations imply we're in an underdensity. And the reason I haven't just shown a single line is because the observations have some uncertainty as well. So this red distribution shows the observations and their uncertainty. So what should be clear is that there's no way that the simulation can reproduce an underdensity as deep as what we observe. So one slight detail here is we haven't simply plotted the underdensity in the simulation. We've enhanced the density contrast by a factor of 1.5, which is the appropriate redshift space distortion factor for ΛCDM. So what I mean by that is observers don't really observe out to fixed distance. For this kind of study, they observe out to fixed redshift, and they assume that they're observing out to some distance based on like some fiducial cosmology. So some kind of assumed value for H0. But because outflows from a local void would inflate the local redshift gradient, out to any fixed redshift, they'd be observing out to smaller distance. So they'd be seeing fewer galaxies, causing them to think the underdensity was even deeper than it actually is. So what that means is that it looks like this point is at a level of about half the cosmic mean, but the actual density contrast is not 50%. We think it's more like a 20% underdensity. But it appears as a 50% underdensity if you're working in redshift space. This problem wouldn't arise if observers use redshift independent distances out to 300 megaparsec. But that isn't quite possible yet. So that's the KBC void. It's not possible in ΛCDM, but it exists nonetheless. So what that suggests is that you should have more structure on scales greater than about 100 megaparsec than expected in ΛCDM. Now, first of all, one thing to bear in mind, normally, we know that due to the impact of structure in the universe, the local redshift gradient should scatter somewhat depending on the exact location of the observer, but this cosmic variance is only 0.9 kilometers a second a megaparsec and is not sufficient to solve the Hubble tension. However, we know that structure formation and therefore cosmic variance must be enhanced to explain the KBC void, which is also reported by these authors. So what I've done here is plotted the apparent underdensity against the ratio of the local redshift gradient to the background value of the Hubble constant. And in general, on average, you should be at this green point, which has no underdensity, and there's no mismatch between the local and global values of H0. But due to the impact of cosmic variance, you could be up here at 5 sigma confidence with some underdensity and some enhancement to the apparent Hubble constant. However, the observations are up here with their error bars. So you can see that you can't explain the observations within their 5 sigma uncertainty, even if you have cosmic variance at the 5 sigma level. However, in principle, if you had a 10 sigma chance underdensity in the early universe, that would more or less solve the Hubble tension and explain the KBC void. Now, of course, the thing is, that's 10 sigma in ΛCDM. In a different model, perhaps this would only be a 2 or 3 sigma fluctuation because the other model has more cosmic variance than in ΛCDM. So try and work with such a model. We use the so-called Milgromian dynamics theory or MOND, which has been covered in previous talks in this series. What we did in our case, first of all, this side is all completely standard. We start with a small initial underdensity at a scale factor of 0.1, when the expansion rate is worked out using the Planck cosmology. So we're assuming a background Planck cosmology. So you get these standard equations where the acceleration is given by some component which arises in a homogeneous expanding universe. So R is a physical coordinate, by the way. Then there's an extra gravity. This gravity comes from the fact that the enclosed mass within that particle, particle's radius relative to the void center, is less than it would have been in a homogeneous universe. This mass deficit, delta M, leads to an outward gravity, which you can work out using Newtonian gravity. What we did, though, because we've already seen that Newtonian gravity doesn't work in this case. It can't explain the KBC void. So we enhanced the gravity according to a formula inspired by MOND, where we've put in the a boost factor, which is also reduced somewhat by the impact of an external field from even larger scales than the void. So this is just a way to jack up the strength of gravity, if you wish, from a given density distribution. So what happens then is you get much faster structure growth. This shows the density contrast on a scale of 300 co-moving megaparsec as a function of the cosmic scale factor A. So roughly speaking, the time since the Big Bang is proportional to A, more or less. So you can see that in the Newtonian models, you get a fairly slow growth of structure. You can have more structure initially, but the growth rate is quite slow compared to the MON models, which are in blue, which grow much faster. So that's basically what the MON models do in this context. Now, what does that mean for Hubble tension and cosmology? So first of all, one important thing to bear in mind is that redshifts arise from three main sources. Mostly people are familiar only with the first source. So lambda obs is the wavelength at which you observe a photon, and lambda emit is the wavelength at which it is emitted. Mostly people know that the ratio between these two is equal to 1 over A, where A was the scale factor of the universe at the time of emission of the photon. However, there are two other contributions that need to be borne in mind. One is a special relativistic Doppler effect. So in other words, peculiar velocity. The other is gravitational redshift, which is important in this case because if we were in a void, then we would be sitting on a potential hill, and therefore photons from the distant universe would be gravitationally redshifted, trying to climb up the hill and reach us. So that would lead to extra redshift. Now, because observers generally don't know about these two terms, they just ignore them, that leads to an incorrect inference for A. So it leads to some delta A, which is a mismatch between the actual value of A at the time of emission of the photon and what the observer thinks A was at that time, based on based on just considering this part. So ignoring the Doppler and GR contributions here. That obviously leads to a biased inference of the first and second time derivatives of A, because they're working with A app rather than the actual A. And that has obvious cosmological implications because they incorrectly estimated A dot. So what happens here is we worked out the apparent H naught and Q naught bar, which is the so-called acceleration parameter, a double dot over A dot squared, that an observer would sort of infer if they're living near the center of a void, and if they assume redshifts are purely cosmological. But we use our void model to work out the redshifts. Then what would happen is you'd get something looking like this for H naught and Q naught bar. So this is the Planck value. And without any kind of local underdensity or overdensity, you'd find this. But the observations are up here with this black point and with these uncertainties. So the uncertainties observational correlation on the H naught and Q naught bar. The void models provide values which are within the 1 sigma error ellipse. So in case you're wondering, the Gaussian and exponential give values which are like, they both at almost the same point. So you can't distinguish the square and downward triangle there. So and the star is here for the Maxwell-Boltzmann profile. So they're all within the 1 sigma error ellipse defined by the observations of supernovae. So void models are nicely able to solve the Hubble tension. Now, one other thing I want to mention is the local velocity field. So we assume basically that the spherically symmetric outflow from a void, which we call V int, plus a systemic velocity of the whole void, which is the V void. So that's in the CMB frame. The total velocity of the CMB frame has to be found by adding V int and V void as vectors. So using the cosine rule. And the local group, we could be somewhere in this range. This is just a schematic illustration. So to try and show you how this works in a bit more detail, this is the velocity field. It's axis symmetric about the x-axis, so you can imagine rotating around the x-axis, rotating this figure around the x-axis. The void's moving towards the left. There's outflow from the void center. So this shows, roughly speaking, the direction of the velocity at any point. Although there's outflow from the void center, the void model has spherical symmetric outflow from the void center. Because of the systemic velocity, the zero velocity point is actually here. So in the CMB frame, it would look like material is flowing outwards from this point rather than from the void center. This black contour shows all the points where the total peculiar velocity in the CMB frame is 627 kilometers a second, which is observed value for the local group. So we would need to be somewhere on this black contour. Now, one argument that's been raised is that the likelihood of a peculiar velocity of only 630 kilometers a second is very small in the void model, because, as you know, the Hubble tension is at the level of about 7 kilometers a second a megaparsec. And if a void has to extend out to many hundreds of kiloparsec, the peculiar velocities would be many thousands of kilometers a second by the edge of the void. And that's certainly what happens in a model. The peculiar velocities are quite large here, as you can see. But within this black region, so this entire region, the peculiar velocity is even smaller than or equal to 630 kilometers a second, which means that a significant portion of the void volume, or a few percent of the void volume, is consistent with a peculiar velocity smaller than observed. So this fine-tuning argument regarding our location of the void is correct, but only at the 2.3 sigma level, which is not really particularly significant. So that's one thing. We found that by considering various observations, there's an overall tension of about 2.53 sigma with all the constraints we considered, many of which make almost no sense in ΛCDM. But in the void model, the overall tension is about 2.53 sigma. That's for the Maxwell-Boltzmann profile. For the exponential Gaussian, you get about 2.8, 2.9 sigma. There is a bit more, but it's still reasonable. Now, when we try to look at the velocity field in more detail, what you can do, okay, so in general, it's hard to find the peculiar velocity because you need to know the Hubble constant to disentangle how much of the redshift is due to cosmic expansion, how much due to the Doppler effect. But inevitably, we're not exactly at the center of the void, which means the apparent expansion rate would depend somewhat on the direction in which you look. So one way to try and quantify this, which we did in Mazarenko et al. 2024, is like this. You would use the average velocity or the average peculiar velocity in a sphere centered on our location. The important thing, so there's a few technicalities to bear in mind. First of all, you have to make do with only the line of sight peculiar velocity because this is what observers have. But you don't treat that as a scalar, you treat that as a vector pointing along the line of sight. That's obviously not the actual 3D velocity vector, but you can pretend it is and keep going. Then you would need to triple the final result because you're only observing one component out of the three velocity components. The consequence of all this is that if all galaxies in the region you're looking at have the same peculiar velocity v, then by following this approach, you would infer a bulk flow of v despite all the projection effects. That's because of the tripling here. The other important consequence is that although a peculiar velocity in general depends on what value you think h naught has, the bulk flow is independent of h naught because changing h naught would affect all the peculiar velocities, but it would do so in a spherically symmetric manner, which would then not affect the average, the vector average within a spherical region. So the bulk flow is independent of the Hubble constant, if you like, of the Hubble tension. So there was this nice astrobite explaining this by Abby and Elena. So if you were to look at the observed bulk flow, then you would get, it's the 3D quantities. You'd get components along the galactocentric X, Y, and Z directions. The main thing is that using the Cosmic Flows 4 catalog, the magnitude of the bulk flow, and by the way, the direction stays pretty consistent within spheres of different radii, but the magnitude follows this sort of green curve, in ΛCDM, the bulk flow on any scale is supposed to be quite small, and it's supposed to get smaller and smaller as you look at larger scales, because there should be less structure on larger scales. So you can see that the observed bulk flows are in significant tension with ΛCDM. This blue line shows an estimate of systematic errors, which are slightly larger at larger distances. So this bulk flow tension is observationally independent of the Hubble tension. Okay, and how significant is this bulk flow tension? Well, the tension, as you saw, gets larger at larger radii. The observations only go out to about 250 over h megaparsec, where h is about 0.7. The tension, the bulk flow tension, is beyond 5 sigma. If you look on scales beyond about 230 over h megaparsec. So this red line is a 5 sigma threshold. And you can see this is the radius within which you're taking the measurements. And this is the likelihood of seeing a bulk flow larger than that observed in the ΛCDM paradigm. So you can see that out to about 140-ish over h, so about 200 megaparsec, there isn't any real tension with ΛCDM. But on larger scales, the tension appears, and beyond 230 over h megaparsec, the tension exceeds 5 sigma, and the data go out to 250 over h megaparsec. So clearly, there is a very serious problem with ΛCDM, which is observationally at least unrelated to the Hubble tension, and indeed observationally unrelated to the KBC void as well. The other thing to bear in mind is that on a scale of 300 comoving megaparsec, you can see that scale in the CMB quite well. We know the temperature fluctuations in the CMB on this scale. This scale is about twice that of the first acoustic peak, so it's very well measured. There's no sign of any problem with ΛCDM on that scale. Or alternatively, ΛCDM is generally calibrated to the observed temperature fluctuations on this scale and similar scales at recombination. So this isn't a question of modifying the primordial power spectrum. That's not going to solve anything. You need some kind of problem to have arisen much later than the epoch of recombination in order to solve the bulk flow tension. So what we did is we investigated the bulk flow in the local void scenario, varying how far we are from the void center, and also the systemic velocity of the void. Without getting into details too much, just want to mention that you want to get a chi-squared less than about 7 ideally, because there's 9 data points from the bulk flow curve and 2 degrees of freedom. That will be the void systemic velocity and how far we are from the void center. Then these black lines show the maximum distance we should be from the void center, beyond which there'd be some anomalous effects on the CMB quadrupole, which rendered solutions right of the red lines, right of the black line, to be unlikely. But we don't know exactly where this black line should be placed. So these are just some estimates. But in general, anything right of this rightmost black line would be quite unreasonable. And if you're left of this black line, it should be quite safe with regard to the CMB quadrupole, with regard to the void model not impacting the CMB quadrupole very much. Now, what you can see, the chi-squared is generally pretty high, but you can have solutions in this dark red region, which are like here. So in short, it is possible to fit the bulk flow curve pretty well with an exponential void profile. With a Gaussian void, it's similar. So if you see the contours have shifted slightly, you would need to be around here-ish for the solution to work. So there is a viable solution, but with the Maxwell-Boltzmann profile, it doesn't really work. You would need to be quite far away from the void center for it to work. That's the chi-squared, but what about the actual bulk flow curve? So with the exponential model, you can see the bulk flow curve is shown in blue. So the solid blue point shows the so-called inner vantage point, the dashed one shows the outer vantage point. with a viable solution. So just to show you the what that means is you have a solution here. You technically also have a solution here, which isn't really reasonable, but it fits the bulk flow curve well enough. Fit the bulk flow curve well enough, the solid and dashed blue lines. The same can be said for the red curves showing the Gaussian profile. That can also fit the bulk flow curve pretty well. And technically, the Maxwell-Boltzmann profile can too. But you can see that the solutions, that the Maxwell-Boltzmann profile requires like a very large distance from the void center, which is not really realistic. And also the outer Gaussian one. But anyway, the main thing is it's possible to fit the bulk flow curve pretty well in the local void scenario. So now we can get on to, before I get on to the crucial baryon acoustic oscillations, I just wanted to mention that you can try to extract H0 from data in some narrow redshift range centered on some redshift Z. So that leads to a so-called H0 of Z. Not H of Z, but H0 of Z. H0 should not, of course, depend on Z, but sadly it does, okay? And that's what the observations show. So any local solution to the Hubble tension predicts that if you were to try and extract H0 from observations at low redshift, you'll get the high local redshift gradient. But if you were to do this from data at high redshift, then you would get the Planck value of H0. We made some assumptions about how observers might go about getting data, converting data at high redshift into a value for H0. But we're showing results here with the so-called model with method 3, which is most similar to the method used by Jia et al., whose results are shown here. There's two studies from Jia et al. Gray is the 2023 study, black's the more recent study, which includes DESI-DR1, but not yet DESI-DR2. The void models, which are most promising, are these red and blue solid lines, which fit the data pretty well. Just to give you an idea, the Schu's value for H0, the local redshift gradient, is in this blue band. The Planck value is this brown line with the uncertainty shown here. These pink bands show the age of the universe from the older stars, combined with value for omega m, which doesn't introduce much uncertainty. The main uncertainty comes from the age of the universe, from like the older stars in the Milky Way. So this is pretty independent of cosmology. So converting that to a value for H0, you get this pink band, which is nicely consistent with the Planck value. The main thing is there is a declining trend from the high local value down to the Planck value, not only in the models, but also in the observations. They're more or less in agreement with each other. It's slightly hard to fit the low point here, but well, the 2023 study has a somewhat higher value. Other thing to bear in mind is that if you compare the solid and dashed red lines, the dashed red line ignores the gravitational redshift contribution, while the solid red line includes it. So the solid red line is what actually the model predicts, but the dashed red line is what it would predict without any local, without any gravitational redshift. So you can see that the gravitational redshift is quite important out here. It's like the dominant contribution. That's because at very high redshifts, when you're far away from the void, there's no real outflow from the void, but there is still gravitational redshift because the gravitational redshift is arising from our location on a potential hill. So there is still an extra contribution to the redshift from that. So anyway, there does seem to be a declining trend in the H0, and several studies have reported a declining trend in H0 with respect to redshift. When they try to infer H0 from data at high redshift, they get a lower value than if they try to do it from data at low redshift. In a sense, that's what the Hubble tension is all about, that H0 inferred from data at Z equals 0 differs from H0 inferred from data at Z equals 1090, the redshift of recombination. Okay, so that's one important consideration, this declining trend. These observations, by the way, involve a combination of supernovae and cosmic chronometers, but also baryon acoustic oscillations. which is what I wanted to talk about next. So regarding the baryon acoustic oscillations, I need to first explain briefly what these are. So this is a graph I already showed you regarding the temperature fluctuations in the cosmic microwave background radiation on different angular scales. This huge first peak, which is quite clearly apparent, even visually, you can see there's a particular scale at which you can see the typical size of these splotches. This means there is a lot of power, if you like, or a lot of fluctuations in the density, in the temperature on a particular scale. Now, at later epochs, this scale should still be evident in the large-scale distribution of galaxies. You can't just have such a large feature in the power spectrum of matter, and this is ultimately in the power spectrum of the baryons. It can't just completely disappear at later epochs. So if you were to plot out the correlation function of galaxies, in other words, the fluctuations in the number density of galaxies against the length scale, in general, you get a smooth decline, as in there's less power on larger scales, but there is an additional bump on top of this smooth behavior, and that defines a particular length scale, or more precisely, a particular angular scale, which is the BAO feature. So the BAO is not about measuring the height of this bump. It's not about assessing whether the overall power law trend is consistent with ΛCDM or not. It's simply about where is the location of this bump in terms of not the height, but the length scale. Thematically speaking, galaxies have a distribution which kind of looks like this. And one way people often discuss the BAO is that you plot out the distance between any pair of galaxies, and you build up a histogram based on all possible pairs. Now, obviously, you could have a small separation between any two galaxies. You could have a large separation. Quite a wide range of separations would arise between any two pairs. But this length scale is clearly quite special, and you would see a huge excess power at that length scale if the galaxies were really distributed like that. Of course, it's not that obvious in the real world, but it is still something we can see and have been able to detect for 20 years. So what are the actual observables? So you can observe the angular scale of the BAO and the redshift depth. So what's shown here is the separation of galaxies along the line of sight. So that will be quantified by looking at the redshifts, and within the plane of the sky, while the distance between them will be quantified based on the angle. And you can see a so-called BAO ring, which is like excess power at a particular radius. So there's a certain angular scale to the BAO ruler and a certain redshift depth. And these are the two observables, okay? The angular scale of the BAO ruler, which corresponds to the size of the ruler divided by the distance to that redshift, and the redshift depth of the ruler, which corresponds to orienting the ruler parallel to the line of sight, essentially. So the redshift depth in a homogeneous model arises without any local void. The redshift depth arises because if you orient the ruler parallel to the line of sight, light from the far end of the ruler must have been emitted earlier in order to get to us. The universe has expanded more in that time, so light from the far end of the ruler is more redshifted. So in short, there's a difference in redshift between the near and far ends of the ruler. The impact of a local void is that it raises the redshift at any fixed look-back time. So at any fixed distance, there's higher redshift, which changes the relation between the predicted angle of the BAO ruler and the redshift. Regarding the redshift depth of the BAO ruler, for the parallel BAO observable, you need to account for how the peculiar velocity differs between the near and far ends of the ruler, because the far end of the ruler is further away from the void center. So it's kind of further out of the void, if you wish. and also the gravitational redshift is higher for the far end of the ruler because photons have had to climb more of the potential hill to get to us. Then there's also the evolution of the void over the light travel time. Now, this shouldn't be such a big deal, but we included these effects, assuming an observer at the void center for simplicity. So that's so these are the BAO observables. Now, first of all, I wanted to present the results regarding the angular scale of the BAO. So that's this schematically illustrated up here. DC is the co-moving distance to some redshift. RD is the co-moving size of the BAO ruler. So what we've done here is we've divided the DC that you get from the observations by DC in the Planck cosmology. So the idea is that you should get 1 in the Planck cosmology, but there is a small uncertainty because the Planck cosmology itself, the parameters are a bit uncertain, but only a little bit. There's like a 0.2% uncertainty in the size of the BAO ruler, according to the Planck results. The observations are shown here. The color indicates which survey was used. The size indicates the year. So more recent studies are published with a larger dot. The void models to pay attention to are the solid red and blue lines. That's the most plausible scenario. So again, we've shown in dashed lines the predictions without the gravitational redshift. You can see that the gravitational redshift contribution is important, especially at high redshift. But at low redshift, the gravitational redshift isn't particularly important. Okay, so the main thing is to focus on the solid red and blue lines and the horizontal line at unity with this gray band. And you can see that in general, the results do line up better with the void model. So that's based on the angular scale of the BAO ruler. The redshift depth of the BAO ruler isn't as clear because there aren't really measurements at low redshift. Measuring the redshift depth of the BAO ruler is much more difficult because there's fewer measurements and they're less accurate. Also, there is the void model predicts a much smaller signal. That's because you're essentially probing the part of the void velocity field where the outflow velocity is declining. Remember, the outflow velocity should rise at first as you go away from the void center, but then it should decline. BAO results are generally only in this declining tail. As a result of that, there's like a cancellation between various effects, between the gravitational redshift contribution and the outflow term. So what the end result is only very small deviation from the Planck cosmology is predicted. So for all these reasons, you can't really tell from the redshift depth measurements whether the void models are preferred over the Planck cosmology, over the homogeneous Planck cosmology, I should say. The void models also assume a Planck cosmology, but it's not homogeneous. You can try to look at the so-called Alcock-Pezinski parameter, the Alcock-Pezinski test, which takes the ratio of the previous 2 plots, basically. So it's alpha perpendicular over alpha parallel. And that could be helpful because it means the results are insensitive to the assumed size of the BAO ruler. In general, the results depend on the size of the BAO ruler, but we've been assuming it's the same as in the Planck cosmology. But if it's different, that would have affected the previous 2 plots. But since it would have affected them in the same way, taking the ratio means that this plot would be unaffected. That's why we're not showing any gray uncertainty band here. However, the uncertainties are raised by taking the ratio between measurements. So observation isn't such a good idea. It's inflated the errors, and you can't really tell which model might be preferred looking at this. What you can do is try to basically average the angular scale of the BAO ruler and the redshift depth in order to get a so-called isotropic average, the so-called DV parameter or distance measure, which is basically calculated in this way. Now, of course, the presence of the factor of z is not too relevant because we're going to divide it by the expected value in ΛCDM. So the factors of z will cancel anyway. The thing is, averaging measurements from orthogonal directions will averaging the measurements from different directions will reduce the uncertainty. So that there's smaller uncertainties, but also in some cases where it's particularly difficult to obtain either the angular scale or the redshift depth of the BAO ruler, it's still possible to report DV. So many studies report DV, but they don't report anything else. So that's why this plot has a larger number of measurements and the measurements are more accurate. So this is by far the best way to look for a signal of a local void. And here you can see that the local void models do fit much better. So we've tried to quantify this in a chi-squared sense in a sec, which I'll show in a sec. What I've done here is, well, first of all, the thing to bear in mind is that baryon acoustic oscillation data were not used to constrain the parameters of either LCDM or the void models. Okay, so BAO data serve as an independent test. As I was explaining earlier, the most discriminative test is expected to be using DV. There's more data, the data are more accurate. So let's have a look at what happens using the DV measure. Based on 42 data points, the ΛCDM model gives a chi-squared of about 76, which corresponds to a 3.3 sigma tension for a single Gaussian variable. It's the so-called equivalent Gaussian tension. The void models reduce that to around 50. This is a very significant improvement. It's a very significant improvement by about 24 to 28. So the void models are more likely by a factor of approximately e to the 12 to e to the 14. However, one thing to bear in mind is that there were 7 studies that only reported the angular scale of the BAO. That means they can't tell you DV, and therefore looking at this column misses those 7 studies. So one thing we can do is quickly combine those 7 studies with these 42 studies to get 49 studies, and then you would get a revised chi-squared, which in the ΛCDM case rises to 93. This is in 3.8 sigma tension. In the void models, you have a chi-square of somewhere between 55 and 57, which means that the void models are able to reduce chi-squared by about 36 to 38. So void models are more likely than the void-free Planck cosmology by approximately a factor of e to the 18 to e to the 19. Which is very large. So void models are vastly more likely than the homogeneous Planck cosmology. Remember, the void parameters were not informed by the BAO data at all. Either, well, they were published 5 years back, so they couldn't have benefited from the more recent data anyway. But they didn't use BAO data at all. It's not that they used only BAO data published until 2020. They didn't use BAO data at all. So that's one thing to bear in mind. That these are testing a priori predictions. These are direct tests of clear a priori predictions. You can try and look only at the DESI DR2. By the way, the previous results all include DESI DR2. But if you want, you can just look at this on its own, if you wish. That will give a less complete picture. But if you do that, then the thing is you can get a measurement of DV and 6 other redshifts at which both DC and DH are measured. In these cases, the measurements of DC and DH have correlated uncertainties, which you took into account. So you get 13 measurements in all. You get 6 times 2 plus 1. At high redshift, the models all agree with each other because obviously a local void is not going to affect things at very high redshift. But at redshifts below about 1, where the void models start to diverge from the homogeneous Planck cosmology, the void models are clearly preferred. So if I try to work inwards, and if you just compare the ΛCDM no void case with the exponential one, you can see that at redshift 2.33, they're both fine. you start to see the void model giving lower chi-square than the void-free model. As you get to redshifts about 1.3, at 0.9, there's a strong preference for the void model, which gets a much lower chi-square. The same at 0.7. At 0.5, the void model did a little bit worse, and the same at 0.3. But there wasn't anything particularly unusual about a few points being discrepant. If you look at the overall trend, the ΛCDM model gets a chi-square of about 31, which for 13 degrees of freedom is 2.9 sigma tension. The void models give somewhere between 1 and 2 sigma tension. The exponential one, which does worse than the Maxwell-Boltzmann or better than the Gaussian, so it's like the intermediate case, gives 1.7 sigma tension. Chi-squared is about 20. That means based on the difference in chi-squared, taking e to the half chi-squared, the exponential void model is about 210 times more likely than no void. You will get a higher number for the Maxwell-Boltzmann, lower for the Gaussian, so this is like the median result, if you wish. Now, this is just looking at DESI DR2. My previous slide was showing, look at all the measurements of the last 20 years, which I think gives a much more complete picture, especially because there's many measurements at redshifts, at very low redshifts, which aren't probed by DESI, but there are measurements of them using other surveys. So that's the DESI result. One other, can I continue for another like 5 minutes approximately? Is that okay? Yeah. All right. So one thing to bear in mind is that the BAO results are discrepant with ΛCDM, as you saw. So just with DESI DR2, there's a 2.9 sigma tension with cosmology. This BAO anomaly has been interpreted as caused by varying dark energy, caused by the dark energy density varying with time. So let's assume for a minute that there is no local void. Redshifts are purely cosmological. Allowing the dark energy density to change with time using the so-called W0 WA parameterization for the equation of state allows a higher expansion rate than in the Planck cosmology at the DESI redshift. So the data basically require a higher expansion rate than in the Planck cosmology. And you can get that with this W0 WA parameterization. But in order to be consistent with the cosmic microwave background, you need to have a period at low redshift when the expansion rate is less than in the Planck cosmology. Okay, to preserve, if you like, the angular diameter distance to redshift 1090. This implies a low predicted H0 of only 64 kilometers a second a megaparsec. That's shown with this yellow line. So first of all, the red contours show a fit to the Planck plus DESI DR2. What's not shown on here is that this doesn't actually fit the data very well. As I was showing on my previous slide, this doesn't really work. There's more than 2.9 sigma tension just using DESI DR2 alone, let alone other older BAO datasets. The yellow contours with the W0 WA model, you can get a decent fit to the Planck CMB anisotropy measurements and the DESI data release too. But in that case, you get this yellow posterior on H0, which you can see peaks further left of the range that was considered plausible for the plot. If you look at the table, then you'll find that H0 is 64 plus minus 2 kilometers a second megaparsec, which is obviously completely impossible given the measurements of the local redshift gradient, at least with the assumption that redshifts are purely cosmological. The other thing to bear in mind is that in order to explain the BAO anomaly, you need a higher expansion rate than in the Planck cosmology, which means you need phantom behavior for the dark energy. In other words, an equation of state less than -1 over a wide range of redshifts, which violates the weak or null energy condition and is generally considered to be very dodgy on theoretical grounds. So it's very hard to explain the BAO anomaly without any local void, assuming redshifts are purely cosmological, by trying to vary the dark energy equation of state. So The other thing which I was looking at is well, which I haven't really looked at yet, but what I want to get onto is looking at supernovae, trying to fit some kind of apparent expansion history, which looks like this, where you take the expansion history in some FRW model with the usual omega m and h naught, but you add like an extra term, which is like a constant times sec function or an exponential decline, perhaps in exponential decline with redshift over some scale of ZC. We tried to do something like this before. I'll show the results in a sec. But the main thing is we want to do a much more detailed analysis where you refit the so-called stretch and color corrections. Because the thing to understand with supernovae is that they're not standard candles, they're standardizable. You have to standardize them based on their stretch and color. The stretch is a measure of how long the light curve takes to decay, and the color is a measure of the color. So we have to refit the stretch and color trip coefficients while also fitting the cosmological parameters and the void parameters, so fitting all of these jointly. The trip coefficients in general are derived assuming no void, but then if you were to use those trip coefficients to standardize all your supernovae and then try to infer whether a local void exists, you might well find that there isn't a void. But this could be a circular argument. So there were a couple of papers pointing out some of the cosmological dependence of supernova analyses, which everyone claims are independent of the cosmology, but they're actually dependent on assumptions about the cosmological model. So yeah, we tried to do some kind of fit like this, and you've got your omega m, you've got your h naught. The red dots show more or less what you might expect in a local void scenario for the Hubble tension. So obviously you'd expect h naught to match the Planck value. You'd expect ZC to only be about 0.2, 0.3-ish. And you'd expect delta h naught to match the level of the Hubble tension, so about 8 or so kilometers a second a megaparsec. And you'd expect omega m to again be equal to the Planck value for around 0.3, 0.31. So you can see that we're marginally consistent with the red dot, at least at 3 sigma confidence. So it looks like we might be able to fit the supernova data as well with a local void scenario. Though the inference on ZC, there is some tension with the kind of with the value of around 0.3-ish that we might expect. It's kind of only marginally allowed. But that's with a completely standard analysis of the supernovae, with the standard sort of trip coefficients. So then, yeah, this is something we're working on, which is the dipole in the redshift gradient. So the redshift gradient differs depending on the sky direction, which is to be expected if you're in a local void, but somewhat off-center. And we fit models, or we're hoping to fit models like this to the data. So that's something that's in preparation. But one important thing to bear in mind is that if you try to analyze the supernova data to infer like a dipole direction, then the LB, well, L is the galactic longitude, B is the latitude. You infer something around here. Well, according to the study by Watkins plus 2023, Watkins et al. 2023 of galaxies, you get a bulk flow in this direction, which is very similar to the direction that is inferred from supernovae as well. So supernovae seem to have they seem to show a similar bulk flow to the galaxies. And also the bulk flow traced by galaxies is in a similar direction to the peculiar velocity of the local group in the CMB frame, which is known very precisely. So these things are all pretty well in line with each other, like literally. That's the last sort of result I wanted to present, okay? Then we get to the conclusions from what I've been explaining in the last hour and a quarter. So the main thing to understand, galaxy number counts across pretty much the whole electromagnetic spectrum, from radio all the way to X-rays and pretty much everything in between, shows that they show that we are in a significant underdensity. out to approximately 300 megaparsec, beyond which the density seems to become more or less flat with distance, and therefore you seem to be beyond the void. But there is strong evidence for a local underdensity, or a local supervoid, if you wish. Supervoids being anything with a size beyond 100 megaparsec. The observed underdensity is not compatible with ΛCDM, so that's just something you have to deal with. But given the nearly uniform initial conditions in the CMB, to get such a large underdensity, there must have been significant outflow. So if you imagine looking at the problem in co-moving coordinates to cancel out the cosmic expansion, there must have been outflow in order to get the density down below the average. This outflow would inflate the local redshift gradient. So the locally measured H0 would be larger than the average, which indeed is the case. That's what the Hubble tension is all about. Naturally, we tried to link the Hubble tension with the local void. It is possible to do so. This is what we did in the semi-analytic void model of Hasselbalch et al. 2020. This was calibrated using many observations, but importantly, not using baryon acoustic oscillation data at all. That means we can use baryon acoustic oscillation data to perform, if you like, a blind test of the Hasselbalch et al. 2020 void model. Or more precisely, the three models, because they considered three different density profiles. Just taking the best fitting parameters in each case, okay? Not refitting them to the latest data. These BAO, the BAO observables deviate from Planck ΛCDM. They deviate from the homogeneous Planck cosmology. Okay, the deviations are as expected in the void model. You can see that by looking at the overall chi-squared, which is about, well, from 49 data points, it's about 93 in the void model, but somewhere around 50. Sorry, it's about 93 in the homogeneous Planck cosmology, where it's only about 50 in the void model. Sorry, it's about 55 in the void models, which is reasonable for 49 data points. So what that means is you are able to reduce chi-square about 36 to 38, which corresponds to a very large increase in likelihood by about e to the 18 to e to the 19. So many, many millions of times more likely. That's for 49 data points, which means that there's an equivalent Gaussian tension of about 3.8 sigma for the homogeneous Planck cosmology, which drops to about 1.1 to 1.3 sigma tension in the void models. We showed that the inferred H0 you get from data at some redshift Z, neglecting the effect of a void, how kind of observers do it, the observationally inferred H0 of the curve agrees pretty well with what you'd expect in the local void model. Because in the local void model, obviously, you wouldn't just put in the cosmic contribution to the redshift. You'd also put in the other contributions and see how that leads to a non-flat H0 of Z curve. But there's pretty good agreement with the local void model for so-called H0 of Z curve. So in short, the declining trend of H0 with redshift reported by many observers seems to make good sense in the void model. Early time solutions to the Hubble tension prior to recombination unfortunately don't work. Obviously, a local void would be a late time solution, but one thing to bear in mind is that you won't be able to solve the Hubble tension at early times. So for example, an early time solution which just has the same shape of the expansion history as the Planck cosmology, but you just compress the timeline 10% in order to boost H0 by 10%, will lead to the age of the universe being significantly less than the ages of the oldest galactic stars. And that's using absolute ages. But if you were to look at cosmic chronometers to constrain Z dot, or the rate of change of redshift with respect to time, that again gives a H0 value very similar to that found by fitting ΛCDM to the Planck CMB observations. So you can see that you're not going to be able to solve the Hubble tension at early times. Okay, so the last point I'd like to make before we hopefully get on to some questions is that very few proposed solutions to the Hubble tension were motivated by something else. They weren't motivated by trying to solve the Hubble tension, and they actually solved the Hubble tension, and they made a successful a priori prediction of something other than the Hubble tension, at least something that's observationally unrelated, that's unlikely in ΛCDM. So in the case of the void, we managed to predict that there should be some anomalies in the BAO observables. And we also, in general, predict much faster peculiar velocities of bulk flows than in ΛCDM, both of which were actually observed. So there's very few proposed solutions to the Hubble tension which have a different motivation and successfully predicted something other than the Hubble tension too, which is also unlikely in ΛCDM. So that's where I'd like to leave it and hopefully take some questions.
Well, thank you, Indranil, for an extremely rich and detailed exposition, which I found absolutely fascinating. I'm going to suggest, since you've been going for just, I think, almost exactly an hour and 20 minutes, that we should take a 5-minute break before we go into the Q&A, just to give people a chance to stretch their legs and make themselves a quick cup of tea or answer a call of nature for some of the older amongst us. So let's come back in exactly 5 minutes. It's 25 minutes past the hour. And then we'll follow the usual convention. Those who would like to ask questions, could you please put a hand in the reaction section? And if you have a follow-up question, a finger. And I'll call them in the order in which I see them, starting with the questions which are already in the chat.
Yeah, can you read out some of the questions?
Yeah, I will, but let's give ourselves a 5-minute break first.
Yeah,
and
sure.
We'll come back then. I will indeed.
Sure.
Okay, thank you very much again, Indranil. Oh, there you are. Okay, Indranil. Indranil is back, so we'll start the questions. And if it's okay, before I call on Veselin, I'll just ask Indranil if you could go through a couple of the questions which are already in the chat, which I'll read out, because not everybody may have seen them. The first is from right back, almost at the very beginning of the talk. And Veselin and also Bernd asked what I think is substantially the same question, which is that the primordial deuterium and helium abundances from BBN are not sensitive to the dark matter components of the universe, and that therefore this well, I'm just reading out the claim in the chat, and therefore the prediction would work as well in a universe without dark matter and energy. You can run the calculation with zero value and get the same result. I think, correct me if I'm wrong, that that's substantially the same point, and that the key is that this is due to the phase of radiation dominance. Do you want to respond to that point?
Yeah, that's true. You can explain the primordial deuterium and helium abundance without dark matter and dark energy. Sadly, you won't be able to explain pretty much anything else.
Okay.
I have objection to that, but we'll see it in the upcoming one.
Okay, I'll call that objection as soon as I call your first question, Jerry. Just two more very quick questions. Janek Kozak would like to know, there appeared a paper that a slowly spinning universe could resolve the Hubble tension. Have you any comments about that? And a second question, unrelated to the Hubble tension, but do you have any comments about the possible connection between MOND and the Pioneer anomaly?
So I can take the question of Pioneer anomaly first, perhaps. That one, there was a paper by Turishev et al. Showing that the Pioneer anomaly is almost certainly not due to any anomaly in the gravitational field of the sun. The Pioneer anomaly arises because of radiation from the radioisotope thermoelectric generator being reflected off the high-gain antenna. That's really what caused it. And this was explained in a nice paper by Turishev et al. In 2012. So I don't think the Pioneer anomaly is real. It wasn't even mentioned in my very comprehensive review of MON in 2022, and nobody asked me to mention it then, despite the wide consultation we did of the whole MON community. And many of the people had actually that I consulted had worked on the binary anomaly themselves, but they don't consider it serious anymore. The other thing is I'm not entirely sure what would be the observable consequence of a spinning universe. I mean, is that designed to? I mean, I would naively think that the centrifugal forces would be larger at larger distances, so it would affect the high redshift universe more. But yeah, I just don't know like what it would do to the BAO observables, for example, or to the local redshift gradient, or indeed to the CMB anisotropies. So I don't know if it would be able to help with any of these things.
Right. Okay, Veselin, your question, you probably want to resume your final question in the chat, but you had a question for Indranil anyway, so please go ahead.
Thank you. Well, first I want to thank you, Michael, for this wonderful seminars. And thanks for Indranil. This is a very interesting presentation of a paper that I had on my desk to read. But I got kind of confused when you actually mentioned Mont. And I was wondering whether you use it subsequently, or that's where you stopped. You just indicated what Mont can do, but then in the subsequent analysis, you did not, or did you use it? I mean, that's what I'm trying to understand.
We use this for the gravitational field. We are assuming at the background level a Planck cosmology and a standard FLRW cosmology with the Planck parameters. Where this comes in, obviously this affects the gravitational field, and therefore the outflow velocity field is affected by the Mond boost, but also the gravitational redshift, which is found basically by integrating g over c squared with respect to distance. So the gravitational redshift is, if you like, for the same density distribution, the gravitational redshift is more than it would have been in general relativity. So Mond is used in several stages to boost the gravitational field from any given density or underdensity distribution.
Okay, great. So that means that it's void plus Mont. It's not just standard kind of considerations without Mont. And
no,
I guess
because
standard consideration would fail.
Yeah, that's right. So if you were to try to explain if you had standard gravity, then you would get some density contrasts, yes, but you wouldn't be able to explain the observed KBC void. So you need some kind of enhancement to gravity to explain the observed KBC void.
Veselin, do you want to come back on that?
Oh, methodology.
Okay. I don't see any other. I don't see any hands at the moment. Roger, yes, please go ahead.
Yes, in the model I'm interested in, you would have a decay in dark matter, perhaps with a lifetime of something like 10 to the 11 half-life, something like 10 to the 11 years. That I was taking might be an argument for to explain the Hubble tension. Is that?
But you're proposing a reduction in density. What you need to solve the Hubble tension, the energy density in the universe at low redshift needs to be higher than in the Planck cosmology.
Yes. Well, how would the decay in the dark matter over? I mean, I guess the Hubble tension involves different times.
Yeah, sure. But the point is that, in my opinion, a reduction in the dark matter density. Yeah. Sure, but a reduction in the dark matter density, so basically the Planck cosmology gives you a good idea of the densities of matter and radiation at early times. There's no real dark energy then anyway. If you have less energy density at late times, by which I mean at the present epoch,
yes,
compared to the Planck cosmology, because you're postulating that dark matter, which was there at the epoch of recombination, has decayed, or some amount of it has decayed, that will reduce the total energy density in the universe, which will reduce the Hubble constant, which will worsen the Hubble tension.
Which will what?
It will worsen the Hubble tension.
Worsen,
yes.
Worse, you think? So you think it goes the wrong way, is what you're saying, is that it?
Yes.
Excuse me, Roger.
Can I-
I mean,
sorry.
In
during
my
your
opinion, I don't know.
question-
I mean, you could try to do detailed calculations of this, but I've never seen studies which argue that, like, so the dark matter is decaying into radiation, I'm guessing then.
It would decay into gravitational radiation.
Sure, but for the purpose of, yeah, okay. But the point is it would decay into radiation species, which decays with, whose energy density decays with redshift faster than matter, right? So it decays as it decays as 8 to the -4 instead of 8 to the -3. So fundamentally, still, what I was saying is still correct, that the energy density would then be less than in the Planck cosmology.
Which would accentuate the tension.
Yeah, that's right.
But can I just say, if I have understood correctly, I mean, what Roger's proposal involves owes nothing whatever to ideas about the recombination epoch, because he doesn't believe in inflation in the first place.
That's right.
It's coming from a completely different theoretical source, which is the.
No, that of course,
Does that not affect the?
Right, but that
I want to recall the Roger's question. Was it related to the age of the universe? Or, I mean, it cut for me the link.
I'm sorry?
We didn't quite
The
understand
age
your
of the
question,
universe,
Leslie.
because for me the zoom. I want to ask Roger to restate his initial question. I got only parts that was related to seconds and units, but I didn't hear what was the whole question.
Well, the question, in the scheme that I'm proposing, you would have dark matter decay. The lifetime is a little bit uncertain, but I was guessing it would be something like a half-life of 10 to the 11 years.
Yeah.
So you'd have a substantial reduction in the dark matter over the period, well, from dark last scattering and so on.
Oh, I see.
If
Thank
I
you.
in
But there
here,
would be no
I
inflation,
think,
yes.
this would be correct. It would enhance the expansion.
You don't know how this works
Yeah,
exactly. I thought the
less-
Friedman equation provides a relation between.
Well, you have
which says-
less energy density, and so the it would drive the universe apart again, wouldn't it?
Is that right? It would. So I think but the Friedman equation provides a relation between the square of the Hubble parameter and the energy density. It says that these are proportional to each other, right? So if you have less energy density, then in general that should reduce the expansion rate. But it depends on the assumption of like the spatial flatness, I suppose, and how much energy density is associated with that.
Well, you have less pullback, right? You have less matter gravitating.
I understand what you're saying. I don't know how this works exactly.
This if dark matter exists, right? So this is the other issue.
But hang on, you've at least initially you've got the dark matter would decay into radiation, so you'd have less sort of gravitating sources in the universe because the radiation would decline faster than the matter with time. I can see why you're coming from. I don't know how this works with the Friedman equation.
I think it will mess up the radiation to matter ratio, and this would kind of shift the location of matter radiation equality.
No, but there wouldn't be any substantial decay of dark matter prior to recombination if to the 11 years.
But all of this talk about recombination, as I say, is presupposing an inflationary scenario.
Well, recombination doesn't assume that, but the CMB anisotropies do require some assumptions along those lines. Yeah, recombination certainly happened in any case.
What is the prediction in cyclical conformal cosmology, Roger, for the? Does it affect this issue about the expansion rate?
I said yes, I would suppose so. I'm no expert on this issue, but according to Christoph, we did look at this question in the paper, which I guess is on the archive at the moment.
Very interesting.
It would be helpful to work out, like, I mean, how do you think the CMB anisotropies come about, and how can you fit the pattern of acoustic oscillations in the CMB in whatever framework you're working in, and what expansion history does it imply? But taking into account also the dark matter decay. You don't need to take that into account for the CMB, I suppose, but you do need to take that into account to get the to work out the angular diameter distance to recombination, right? And then you need to work out the apparent, well, the expansion history, the value of A dot today, and whether it might help with the Hubble tension.
Well, I know, all I know is that in the paper, I mean, it's not my part of the paper, and I don't know these things, but Christoph does claim that there would be, it would provide a possible solution to the Hubble tension issue.
Well, can you share like a preprint number?
I was going to say, is there any chance you're sharing that paper for us in the?
Oh God, I don't know how to do these
No,
things.
it's okay. But perhaps.
But if you just
I
read
tell you
it
what,
out
after the meeting, I'll just get the details from you and put them in the.
Or if you just read out the archive number, I can find it.
Yes, we'll find it. It's okay. We can look it up. But don't worry, Roger. We can.
Okay.
We can easily trace it because we know the authors.
Okay.
Thanks very much. Are there any follow-ups to that or question or?
I think
I have a second question about the use of the Planck parameters.
Yeah,
the
go
Hubble
ahead.
parameters. Basically, in the slides, in the subsequent one, you were using the little h, and I assume this was coming from Planck.
Which little h?
I'm not. Yeah. I mean the normalized Hubble parameter.
Oh, you mean on plots like this?
Well, it was further a little bit before the BAOs. Yeah, like here. And then after that, I was wondering, presumably this is Planck, but what happens if you use the local measures?
That won't affect the result very much, because that will simply affect the cosmic timeline a little bit, and it'll slightly affect the predicted density fluctuations in ΛCDM on those scales. But it will not meaningfully affect the fact that the bulk flows are approximately quadruple the expected value in ΛCDM.
Mm-hmm.
In general, the bulk flow tension is pretty independent of the Hubble tension observation.
Okay, so that it's basically you're using there mostly the Planck value because there is not much effect.
I think they use the Planck value to the Planck cosmology to work out the expected level of density fluctuation, and therefore the expected bulk flows in ΛCDM. So in short, for this curve, I think is based on the Planck cosmology. But if you were to use a different cosmology with like 10% higher H naught, that would barely shift the red curve.
Okay.
And the observed curve, of course, would not shift.
And if there is no more questions, then probably I can ask my last question.
I don't see any more, so do please go ahead.
Okay. The evidence of the redshift. I mean, usually the Planck parameter, of course, depends on that. But you were showing a slide that indicated, depending on what kind of data one is uses, then they can see how from local you can move towards the Planck value. Effectively,
you mean here?
Some kind of Z dependence.
Yes, there is. Well, the Planck value isn't used in any of these points, by the way.
Yeah. Right. So I was wondering if you deduce dependence here and then use it for the BAO oscillation and subsequent slides. I mean, did you try to do that, or you were doing it?
Well, we're using the same model in all cases, right? The same void parameters, for instance. So is that what you're asking?
I'm trying to figure out. I mean, so you deduce the Planck parameter dependence on Z based on the void, and then this is what you use for BAO and the other.
Yeah, that's right. The
tensions.
same models that are shown here in these red
Okay.
and blue curves it's the same models that we showed in all these plots in the red and blue curves. It is the same void models.
Okay. Okay. Thank you. I have no other questions.
Great. Thank you very much indeed, Vaseline, for very, very interesting clarifying questions. Jarek, did you have a question? Sorry, I thought you just unmuted yourself, but I didn't see a hand.
I think someone put in a comment on which was the preprint Roger Penrose was referring to.
Good. Did they? I didn't see that. That's very good, because I was going to look it up. Let's see, is it there at the bottom? Yes, there it is. There it is. George, George, thank you, George. Thank you very much indeed. Good to have you with us. Thank you very much indeed for that. I certainly want to look that up and study it.
Yeah, so this one you must mean, right?
Yes, that's right. The archive 256.3.24263. This is this is the joint paper on cyclical conformal cosmology with Christoph. Sorry, I can never remember the name of Roger's co-author. Sorry, but anyway, it's that is the Arxiv number. It's in the chat. Okay. Do we have any other hands? Do we have any other questions or any follow-ups to questions that have already been asked? I don't see any. Well, rather than bring things to a premature end, is there any final summing up that you'd like to give, Indranil? If there's, if you would just like to take another 5 minutes before we close the meeting, in the absence of any questions.
Well, just to all I'd say is like I've been working on the void model for about 5 years-ish, and we originally came across it not because of the Hubble tension, but because of the galaxy number counts from Keenan, Barger, and Cowie, but also many others papers over the last last 35 years have shown evidence for a local void. So initially we were just hoping to quantify the likelihood of such a void in LCDM. It's only as we were starting to work on the article that we realized that that an underdensity would inevitably create gravitationally driven outflows, which might enhance the local redshift gradient, and that this might solve the Hubble tension. So then we changed. We made a semi-analytic model of the void and of gravitational outflows from the void. So it's a self-consistent model, if you wish. We made that the main focus of our 2020 paper. So it ended up addressing the original aim of quantifying the likelihood in ΛCDM, but this became like a major extension to it, which I was very happy with. But then, of course, it became difficult to find additional tests of the model because it already tried to fold in the data that was available. We hadn't folded in BAO data. So one thing that I was advised about in St. Andrews when I was there a few years back is that the void model might not work with the BAO data, which makes sense, but people hadn't really looked into this. So that's why I thought like the BAO data would be a nice sort of independent test of the void model that we hadn't used to constrain the parameters. I need to sort of check if it would actually work. So yeah, much of the work was actually done by a summer student, Vasileios Kalaitzidis, and I'm sure we'll be making the slides available later on, I hope. But basically, we've submitted a preprint on the BAO test of the void model. And this is, I think it's very nearly accepted by now. So this shows, especially with the latest DESI results, that there is a deviation from ΛCDM what I found really interesting is I had, of course, thought about like what the BAO observables should look like in the void model, what the prediction is. I thought about that. What I had not really considered is if the BAO observables did line up with the void model predictions, that it might sort of plunge cosmology into a crisis. I hadn't thought about that, but that's basically where we seem to be. And the other really remarkable thing is that in order to solve this crisis, which is quite different in its nature from the Hubble tension, as in it's a different issue observation to the local redshift gradient. One remarkable thing about it is that the DESI team went ahead and published like how they could fit the BAO anomaly by assuming not ΛCDM but this W0 WACDM, where you have like a varying equation of state for dark energy. But they carefully hid the fact that their model predicts H0 of 64 kilometers a second a megaparsec. So once people realize this, it'll be clear that basically any kind of attempt to solve the BAO anomaly purely by adjusting the background expansion history will not work, because the BAO anomaly requires a higher expansion rate than the Planck cosmology at intermediate epochs. But to keep the same angular diameter distance to the CMB, you have to have a lower expansion rate than the Planck cosmology at very low redshifts, which will worsen the Hubble tension.
It's very interesting indeed. If I just say very, very quickly, I mean, wearing my kind of ex history and philosophy of science hat, there does seem to be a very interesting kind of methodological takeaway message from all this, which is that cosmology as a as a case study for the way in which the parameter space of models is constrained and unified, or remains very far from being unified. It makes, well, as I say, makes a very, very interesting case study, because in both the case of the Pioneer anomaly and indeed the Hubble tension, you have obviously a very complex parameter space, which is parts of which are extremely model dependent, other parts of which are really locked into some very very fundamental assumptions about background assumptions, which seem to be not so model dependent. And it's a very, very challenging, very, very challenging task to try to sort out just what the methodological prerequisites are in even approaching the question of how one should think about constraining and unifying this parameter space, let alone, of course, in actually testing the models which result.
One thing that's
I think it's far beyond anything that one sees, for instance, in particle physics, in terms of the subtlety of the methodological issues.
It's very tricky because you're stuck with the observations. You can't really do experiments. Yeah. But one important thing to understand, like people often sort of confuse the issues of constraining the parameters of a model, yes, which it makes sense, but only if you have a very high degree of confidence the model is actually correct.
Exactly.
And also, just trying to constrain like what's the actual parameter. Like, for example, you could think that Kepler had like definitely the correct idea for the solar system, but you just need to constrain the actual value of the astronomical unit to like get the absolute scale. So that's like that would be a reasonable task. And you could do that either by looking at Earth's orbit, or in principle you could do that by looking at Venus' orbit or Mercury's, because Kepler had precisely given you the ratios between all these things. Yeah. You wouldn't expect any kind of discrepancies to arise. Like,
well, he was predicting, obviously, very much from ab initio, from a priori convictions about platonic solids in modeling reality. And of course, his predictions were, unfortunately, didn't quite get it right. Otherwise, we would have been home and dry in one bound. But I do take your point. I think there's some very interesting stuff.
What I was trying to say is that there's a distinction between like trying to.
Sorry, you're fading.
Sorry. What I was trying to say is there's a distinction between trying to constrain the parameters in a model which you have a lot of faith in, yes, versus like testing if the model is actually correct. Yes. That's a rather different task. One has to distinguish like which one is trying to do. You could definitely write articles which say, like, assuming this model is correct, what must its parameters be? But that's a very different task from trying to say, like, is this even the correct model in the first place?
Yeah, that's exactly what I had in mind by saying distinguishing the bits of the parameter space which are model dependent from those which really do rest on much more general, and background assumptions that we're much less willing to give up. No, that's pretty well what I had in mind. But you're saying it much more clearly. You're saying much more clearly as a practicing astrophysicist what I was just kind of groping to try to say in a very vague, handy baby history and philosophy of science methodology focused way. But yes, no, I agree. So there are many ramifications of this issue which go far beyond the fine detail of the astrophysical models, interesting as those are. So thank you for a very rich and very interesting talk, and definitely no more follow-ups, no more questions anybody has. Well, if so, thank you very much again, and to all the questioners, and we'll see you again in